All right, so last week we finished, yeah,
I was wondering if you could go back a couple slides.
yeah. Where do you want me to stop?
You'll know.
I'll know?
You should. Just keep going. Oh, no. Nope. No, it's not there.
What are you looking for?
Nothing.
No, tell me. So what do you mean nothing?
You should learn.
You started this. What do you
I don't really want it to start from the beginning. You'll find out another day.
Oh, no, I'm too curious of a person. You gotta tell me. What's going on?
There was supposed to be a picture of your dog from Mason.
Today.
Is it? Did he put it in my slide?
I don't know. He said he did.
I don't know which
That's
slide.
why he was going around.
Oh.
Maybe some other lecture. But he put it at the top.
You know, the ones that you had pulled up on your computer when Mason was snooping around.
Okay, it might be the other lecture. What is this? I don't know. Do not disturb, say yes or no?
Yeah, so that none of your email things come up when you're on.
Oh, I don't know. Okay, so let's see what he did because he was laughing every time I walked by him. He was just laughing.
He said 23. He said he put it. Oh,
There
there it is.
No, he said that he messed up and he thought,
Ah.
oh my goodness.
Okay, my son.
The previous lecture.
I was like, I thought that you had a question about something. Okay. All right, so back to this. So we kind of started a little bit talking about functionality, but as of now, this is kind of our outline again of what we're covering in the class. But as of now, we finished talking about protein structure in terms of intrinsic factors. And we talked about a lot about ways to characterize protein structure. So we spent quite a bit of time. You worked on 2 practice problems. And now what we want to do is move on and talk about how the structure impacts the function upon processing. And how with the intrinsic factors impact how the structure change in terms of molecular configuration, molecular size, association and interaction, and surface properties. So we'll give more examples on how the structure in particular changes with extrinsic factors and how does that impact functionality. So that is the next focus of our series. And the first thing that would happen when you impart extrinsic factors such as, let's say, temperature during processing, we get denaturation. The protein structure changes, and we refer to it as protein denaturation. So I'll be talking a little bit about protein denaturation and how the different factors impact protein denaturation and how will that result in structural and functional changes. Okay, so this is kind of an overview of what we will cover in this topic. Just a little bit of, hi, Serpo. Serpo's here. Okay, so just a little bit of why processing is required. So obviously, food is processed to have different outcomes. One important outcome is inactivation of enzymes. So let's say lipoxygenases, for example, or enzymes that impact color, or enzymes that result in off-flavor production. So we usually target enzymes to be inactivated by thermal treatment. And obviously, destruction of microorganisms. So food is thermally treated for inactivation of problematic enzymes and obviously destruction of microorganisms. Also development of flavor and texture. So when you heat the food, eating raw meat is not as flavorful as eating cooked meat. So basically developing flavor and texture, and also destruction of toxic compounds. So degradation of compounds that might otherwise be harmful to us, then thermal degradation would get rid of that. And then improvement of nutritional quality in terms of, if you think of not just protein, starch. So if starch is raw starch, it won't be as digestible. It won't be digested as gelatinized starch. Same with protein. A little bit of heat unfolds the protein, therefore the protein will be more susceptible to digestion or digestive enzyme. Okay, so processing is required. There's no way around it. We process the food we eat. And this processing can result in desired and undesired changes, in particular to protein functionality. Can we think of desired changes? Lisa?
Browning?
Okay, the browning can be desired and can be not desired. So I have it later. Desired in like baking of bread. It's desired through the Maillard reaction. But it can be not desired in a beverage over time, that you have a reducing sugar and you have protein, and then over storage or during heat treatment you get Maillard reaction and browning that might not be desired for that beverage application. Okay, what else? Desired, not desired. Huh?
Like for doughs, there's like desired and not desired, maybe like needed and stuff.
Okay, yes, definitely. This is physical modification of the protein. So it is desired to unfold the protein and help develop the three-dimensional network of the gluten. Okay, good. I didn't have it here. It's coming up. I didn't have it here, but it's a good example. Yeah?
Would it be like if you have unfolding of proteins and you're exposing more of the surface, you could increase emulsifying?
Yes. So partial unfolding can enhance emulsification, can also enhance thermally induced gelation. So you might actually get an enhancement of certain functionalities. Good. What else? We talked about improvement of digestibility, but is there reduction? Could there be a reduction in digestibility as well? Yes, so excessive heating and excessive processing may lead to polymerization of the protein, and a polymerized protein, that means a big structure of protein, will be less easily digested due to limited enzyme accessibility to the bonds. So let's see what I have here in terms of desired and undesired. Yes, Katie?
So would that mean if you overcook your food, like chicken, then you wouldn't be getting enough protein? Or is that maybe more?
So with meat protein, it's a little bit different. It's more easily digested than any other protein, given that you don't have as much disulfide linkages formation, and it's a very hydrophilic protein. So it's kind of a strand. You don't have that much of hydrophobic. Hydrophobic residues are really low in concentration, so they don't form this large aggregates of a protein. It's still digestible when you cook the meat. But if it is soy protein, for example, and you thermally treat it excessively, it will form large aggregates and you would reduce digestibility. Due to the fact that soy protein has higher hydrophobic residues and also have more sulfidal groups. Good question, though. All right. Okay, let's see what we have. Desire, we didn't talk about thermal denaturation of trypsin inhibitor, for example. So soy needs to be thermally treated in a way that over 90% of trypsin inhibitor has been inactivated. Kind of this is a rule, because trypsin inhibitor will mess up our digestion because we have trypsin in our digestion tract. And if we have inhibitors that we're consuming, we're inhibiting our digestive enzyme, causing problems with digestion of proteins. We talked about improved digestibility, better emulsification and foam, better heat-induced gelation, obviously. The undesired is in a beverage, you thermally treat the beverage. If it has a protein that denatures at low temperature or temperature similar to pasteurization, then we are denaturing them, and over storage they're going to be polymerized, and especially if you have high protein inclusion level, then it would be forming a precipitate due to insolubilization. And we talked about loss of digestibility due to irreversible denaturation. That means the protein is denatured and polymerized.
Is there any way in processing that you could break some of the peptide bonds that would increase solubilization or no?
Processing to break peptide bonds, you don't usually break peptide bond without an enzyme or acid or alkaline with heat. Just heat treatment does not necessarily break your peptide bond. It's a very high energy.
Not even at really high or low pH?
Well, pH, yeah. If in the presence of acid and alkaline and heat, yes, you're breaking peptide bonds. Yeah. Yeah. And that's when I have the Maillard reaction. Sometimes it's desirable, sometimes it's not desirable, and we talked about that. Okay, so we process food for multiple reasons, and the impact on the protein is sometimes good and sometimes not good. And the impact on protein is mostly has to do with its denaturation, changing in the protein structure. So just a reminder about protein denaturation in terms of changes in the native structure. So we know that when the peptide, polypeptide is formed, you have a lot of free energy. So the free energy and that is unstable state. In order to come to a stable native state, we have a lot of containment of energy through bonding. So the enthalpy goes up and the entropy goes down. So when that happens, your delta G is positive. Okay? So then when you have delta G positive, that means you have a stable state for the protein. Anything that will result in increase in entropy, breaking of some bonds within the protein, will result in generation of free energy, and when this value is increased and the enthalpy decreases, then you have a negative delta G. With a negative delta G, that's spontaneous denaturation. Okay. So back to the role of water and denaturation in this case. So what happens here is when you have protein usually is an aqueous medium. In an aqueous medium, you have your peptide chains orient their hydrophilic amino acid towards the outside and hydrophobic towards the inside. And the water forms around the protein. And especially if you have hydrophobic regions, what you have is the water forms kind of a crystalline structure around the protein, resulting in low entropy, maintaining the structure of the protein. That is at native or normal conditions, not non-processing condition, no heat treatment at this point, or any denaturing agent at this point. So water is excluded, as we say, from the interior. It forms structures around the protein, stabilizing the protein and reducing the entropy. The more you have water-protein interaction on the surface, the more the protein is stable. Anything that will destabilize protein-water interactions will cause faster denaturation of the protein. So basically we assume a structure, the protein assumes a structure or configuration that minimizes free energy. This is just to remind you that the stabilization of a tertiary structure is entropy driven. It's similar to what we say. Any change in entropy will result in a change in delta G, obviously. So if entropy is reduced, delta G is positive, so no denaturation, it's stable. Denaturation is unfavorable, especially at low temperature. When we increase the temperature and break bonds within the protein structure, the delta S will increase, delta G becomes negative. Just making sure you you get that this knowledge. Keep that knowledge in mind. So, at high temperature, denaturation occurs with exposure of hydrophobic groups to water. In this case, delta G is negative and denaturation is spontaneous. So what happens at higher temperature, we have higher thermal kinetics within the polypeptides that facilitates unfolding. So the bonding that actually stabilize secondary structure and also tertiary structure, such as hydrogen bonding, electrostatic, van der Waals, they are exothermic. That means they, with high heat, they become unstable. Okay? Whereas hydrophobic are endothermic, so they are stabilized more at higher temperature. However, at increasing temperature, what happens is the water structure around the protein breaks, destabilizes, and then when the water structure is destabilized, unfolding becomes more spontaneous. And you can interrupt for questions. Yes, Lisa.
So even though hydrophobic are endothermic, they'll still break down at higher.
Due to the breakdown of water structure. Because the water structure formed a crystalline type of ice-like structure around the hydrophobic regions. So with the increase in thermodynamics, the water structure gradually breaks down. And when you don't have water structure formed around the protein, hydrophobic groups no longer need to hide from the protein. So they have the tendency to be exposed. And that's kind of the...
So there's really just like a narrow range of where it's the most stable?
Huh?
So does that mean there's just really a narrow range of where it's most stable?
Yeah, well, narrow range, and it really depends on the percent hydrophobicity of the protein. And that's why different proteins denature at different temperatures. So whey protein denatures at 70 degrees, whey protein, soy protein can denature at 80 and 94 depending on the different subunits. So that has to directly relate to the percent of hydrophobicity. The higher the hydrophobicity of the protein, the higher the denaturation temperature. Okay. And to that effect, I kind of answered some of that by asking, how does amino acid composition affect thermal stability? So if we look at these two different proteins here, we have the whey protein and the quaternary structure of casein. If you see here the arrows, do you remember the arrows indicate what in the structure?
The sheets.
Bereshit, yes, you are studying. And the helixes, here, alpha helix. And the helixes, alpha. Okay, so this tells us you have a lot of ordered structure that is stabilized by hydrogen bonding. And hydrogen bonding is weakened by heat. Okay, so that this denature at 70 degrees or higher. If we consider the casein, I should have put the structure of an individual casein up, but it is higher in hydrophobicity, and the structure is mostly stabilized by hydrophobic interactions. So they will withstand higher temperature before denaturation. So casein, for example, denatures at 140 degrees up, whereas beta-lactoglobulin denatures at 70 degrees up. So the composition, again, plays an important role in the denaturation temperature of the protein. If you have questions, you can always interrupt. That's okay, you'll have less material to study for the exam. Okay, so how does water play a role in denaturation? So dry protein powders are extremely stable. However, once you start increasing the moisture content, then denaturation occurs at lower temperatures. So look at this graph here. So you have denaturation temperature here, water content. So as you increase water content, you can see that the denaturation temperature decreases. Decreases dramatically, and then it plateaus out with additional water. So what happens is that when you have water in the system and you're heating, the thermal kinetics makes the water more mobile. It moves and it penetrates into the cavities of the protein or the interior moiety, causing swelling. Then what happens? When the water migrates inside of the protein structure in the interior, and what happens, do you think? Think of what we talked about earlier, that the water is expelled, and then what happens?
The hydrophobic bonds and exposed.
Sure, but what caused them to be
The
exposed?
hydrogen bond.
Hydrogen bond. What happens to the
The
hydrogen bond?
water will compete with the hydrogen bond.
So the water, instead of the protein interacting, or the protein residues interact with each other via hydrogen bonding, stabilizing that structure, water going in will then form hydrogen bonding inside and break the hydrogen bonding, and unfolding starts to occur, and hence the swelling here. And then the hydrophobic groups, like Patty said, will be exposed. So, but the start is water will start competing for hydrogen bonding. Okay, so the denaturation process is a cooperative process. What does that mean? That means once few bonds are broken, once few hydrogen bonds, let's say, are broken, then there will be distance. The distance will grow between the amino acid residues. Then when you have larger distance, then other bonding are going to be broken. So hydrophobic, electrostatic, so that you will have a cooperative process of denaturation. Only, if you remember, only 2 to 3 bonds, hydrogen bonds, are when they're broken, entropy increases dramatically and delta G becomes negative. So hence here you see, okay, let me explain the y-axis. The y-axis is any property you are measuring as a factor of a denaturation condition, either a denaturant concentration, temperature, or pH. So let's say we are measuring surface hydrophobicity. Surface hydrophobicity will increase with denaturation. If you were measuring solubility, solubility will decrease with denaturation. But this steepness here in that curve tells you that it's a cooperative process. So once one thing starts to happen, once few bonds are broken, everything will break loose, basically. And you see that steep point here, or steep increase. Okay, so what is, again, back to protein denaturation? In simple terms, it's unfolding of the protein. So basically breaking these bonds and having the polypeptide separate, not be in close proximity or in compact structure. It just starts separating and unfolding. So when fully denatured, a globular protein that was originally in compact, well-structured, stable form becomes kind of most likely a random coil kind of structure. So denaturation of a protein is when there is a loss of quaternary structure. So some proteins, like casein, is stabilized in a quaternary structure. Some soy protein is stabilized in a quaternary structure, so that you have multiple subunits linked together to form a certain quaternary structure that is stable. So anything that will cause breakdown of that quaternary structure is considered denaturation. So denaturation can occur at a quaternary level. It can occur at a tertiary level, where we are unfolding one subunit, one particular protein unit. Or it can occur at a secondary structure, so changing of the beta sheets to random coil, or conversion even of an alpha helix to beta sheet. That's also a denaturation. That's also changing the native structure of the protein. It can be reversible or irreversible. Okay. So usually short-term action, which cause partial unfolding, is reversible. So I have here a rubber band with me. Think of this rubber band as a protein. Okay, I'll explain it in a simple term regarding the rubber band. So you have rubber band, it's elastic. So you hold it and let go, it goes back to its original state. Let's say you were playing with it and you just did this for the longest time possible. What's going to happen to the elastic? Will it go back to its original? No. So that becomes irreversible. So forget about the elastic, think about the protein. If I heat the protein for an extended period of time, or if I subject the protein to low acid for an extended period of time, or high acidity, high alkalinity for an extended period of time, then you're most likely causing irreversible denaturation. However, let's say you took milk and you put the pH down to 4.6, and you will see some sedimentation of the casein. Change it back to 7, then it will become soluble again. However, if you heat it a little bit, keep the pH at 4.6, the protein gel starts forming and forming interactions with forming a matrix that will be irreversible to bring it back to soluble state. Okay. Now, protein concentration on solutions plays also a very important role in irreversible denaturation. Because what happens if you have 0.1% protein versus 5% protein? If you have 0.1% protein and then the protein is denatured. It's in solution, but it's denatured. 0.1% protein, you will have very small amount of molecules that are bumping into each other. You have to think these molecules are always they're dynamic, there's movement, right? So the chances of them coming in close proximity to each other is lower than if you have 5% protein. Then you have more protein in the solution, the chances of them being in closer proximity to each other is higher. So if you put denatured proteins in closer proximity to each other, what's going to happen? What's going to happen is polymerization. Why? Because when you have close proximity of proteins that are unfolded, so you have a lot of hydrophobic groups exposed, and they're close proximity to each other, then they're going to attract each other and form hydrophobic interactions to get away from water. And not just only hydrophobic interactions, if a protein is unfolded, then you have the free sulfider groups are going to come in close proximity to each other. And disulfide linkages are induced or formed more under high temperature and pH. So if you have the right conditions and the protein is in close proximity to each other, then not only hydrophobic interactions can form, but also disulfide linkages. And once these interactions are formed, they are irreversible. And that's where denaturation becomes irreversible. Okay, so denaturation and renaturation. So let's say we have a native protein. And that protein has a lot of disulfide linkages, and we put a reducing agent and also a denaturing agent, which is urea. So urea will break hydrogen bonding because urea is a reagent or an organic reagent that forms hydrogen bonding. So it will break hydrogen bonding within the protein molecule. So basically, once you do that, once you put beta-mercaptoethanol, which is a reducing agent, you're breaking disulfide linkages and you're breaking hydrogen bonding, so the proteins unfold. But if you do that for a short period of time and then you take those out of and you remove these denaturants, then you might go back to somewhat similar native structure. It might not be the exact structure, but somewhat similar. However, irreversible is if you add performic acid So the performic acid react with the sulfidyl groups, forming cystic acid. Once this is formed, you can no longer go back to form disulfide linkages. So this is irreversible denatured protein. Okay. pH. So what happens when your pH is at its extreme? Either very high pH or very low pH. At this point, you get like charges. So most likely, your protein will have a really high net positive charge if it is very low pH, or really high net negative charge if it's really high pH. With like charges, you get repulsion within the protein. So you break electrostatic interactions, and then once electrostatic interactions are broken, again, a distance is going to grow, and when the distance grows, other interactions are going to be broken. Hydrogen bonding, hydrophobic. So, and then you get the swelling because the water starts going in, interacting with those charges, because you have really high charges, so water goes in, swelling occurs, kind of like, again, the cooperative process of once one type of bond is broken, or hell is broken loose. So everything else gets broken. Okay. However, on another effect of pH, if the pH is at the isoelectric point. So if the pH is at the isoelectric point, such as acid curd, generation of the curd in milk, here in this case you lost charge. And when you lose charge, obviously you lose interaction with water, and you start the proteins start interacting with each other via hydrophobic interactions because you don't have any more repulsion. And however, again, it's mostly reversible. If you bring back the pH to neutral, you can solubilize unless it has been unless the treatment took longer time. Other types of denaturation, a pH can cause partial hydrolysis depending on the presence, the temperature. Peptide bonds can be broken. That's the primary structure. So primary structure of the protein, also when you break peptide bonds, it's also denaturation because you again change the conformation of the protein, so you would change other interactions that were originally present in that protein that got broken. Deamidation of asparagine and glutamine. When it's high pH or high or low pH, asparagine and glutamine become aspartic acid and glutamic acid. So that is a change in the composition of the protein which will impact structure formation. Destruction of sulfidyl groups at alkaline pH, that you can form disulfide linkages at alkaline pH, causing aggregation, and which result in irreversible denaturation. So changes in pH can impact so many different things. Not only just changing the charge, but can also cause breakdown of peptides, the deamidation and the destruction of sulfidyl groups forming disulfide linkages, aggregation, and so on. Okay? All right. So salt have two-sided effect, depending on the concentration and the type of salt. Not just the concentration, type of salt is very important. And also type of protein, because different proteins have different charges and they would interact differently with the salt. So a small concentration of salt actually helps solubilization of the protein. That's why if you take any protein beverage, you might see phosphate salt in there at a small concentration that is added to enhance solubility of the protein. So with a little bit of salt, what happens is you are increasing the charge load on the protein. So salt is interacting with the protein on the surface via charge interaction or electrostatic interaction that actually can drive water to interact on the surface of the protein, enhancing solubilization. However, if you increase salt concentration beyond a certain point, what happens is total shielding of charges and competition for water, interaction with water. So, which will result in protein actually unfolding, because when the protein charges are shielded, they're no longer interacting with each other. The amino acid groups are no longer interacting with each other via electrostatic interactions. The salt is taking over and resulting in breaking of electrostatic interactions. So causing these proteins to open up and aggregate with each other rather than interact with water, in addition to the salt competing for water. And this usually happens at ionic strength of 0.2 or even lower, depending on the charges of the protein, or the load of the charge on the protein itself. However, at higher concentrations, higher than 0.2 ionic strength, say at concentration higher than 1 molar, what happens is not just the protein no longer interact with water and the salt is competing with water, we're getting structural instability of the protein itself. So there are 2 types of salt. One salt category that actually stabilizes the protein at low concentration by enhancing hydration, and it binds weakly to the protein. A different type of salt will bind strongly to the protein and destabilize the structure. Let me illustrate. Okay. So this is a diagram that shows denaturation temperature. Okay, at concentrations less than 1 and greater than 1 molar. So not only the protein here is not interacting with water anymore, we're causing a structural change. So here's just beta-lactoglobulin, and here are salts of sodium. So sodium chloride, sodium bromide, sodium cyanide. So what you have here is the effect of the anions. So the chloride, the bromide, the cyanide. So the impact of the anion is more significant than the impact of sodium, because these are all sodium. So it's the same positive ion but different negative ion. So the negative ion is impacting the way it's interacting with the protein. So what you see here is as salt concentration increases, denaturation temperature decreases. And for example, the sodium cyanide, which is the rectangle here, has a great impact on denaturation temperature compared to sodium chloride. Okay? So here what happens is at low concentrations of sodium chloride, for example, you get the denaturation temperature to increase. So sodium chloride is actually causing some stability to the protein structure, whereas others are causing destabilization of the protein structure. So, so we have what we call cosmotrope and catotrope. You might have heard of these terms before. So a cosmotrope is a solute that actually stabilizes the structure. How does it stabilize? It binds weakly to the protein and actually causes an osmotic pressure where the water drives towards the protein. And then when the water is around the protein, the hydrophobic components within the protein don't really want to show up anymore. There's a lot of water, so denaturation temperature increases. So you have a lot of water around the protein. On the other side, you have the catotrope. The catotrope is where you have a type of salt or solute, not necessarily salt, that will bind so strongly with the protein, and the water is kind of pushed away. When you don't have water anymore surrounding the protein, the hydrophobic residues give them a little bit of temperature and kinetic energy. They're going to, okay, there's no water around anymore. I'm going to open up more easily. Okay, so examples of that, so sulfate, phosphate, and fluoride. So that's why you would see phosphate in beverages. Okay, phosphate salts, you actually act as cosmotrope. So they will enhance the solubility of your protein. Whereas if you add salts of bromide, iodide, perchlorate, and cyanide, these will bind very strongly to your protein, resulting in reducing denaturation temperature and destabilization of the structure, because you lost water, and water is a big factor in reducing entropy. Remember that, the structures of water around the protein. Okay, other examples, so this is in this, I'm just showing you salts, but there are other examples where small sugars, for example, glucose, sucrose, can act as cosmotrope, stabilizing the protein, whereas other components like guanidine HCl can act, guanidine HCl or urea, can act as chetotrope.
Here's a small experiment we did in at Purdue in one of the food chemistry labs. And we looked at impact of salts, sugar, and acid on the denaturation of albumin, which is egg proteins. So we heated the albumin, and then we looked at the temperature, we jotted down the temperature of opalescence when we started seeing cloudiness. And that's an indication of denaturation of the protein, when the protein starts denatures and start gelling. So with just water, temperature of opalescence is at 85. With added salt at a particular concentration, we got reduction in denaturation temperature. However, with ferric chloride instead of sodium chloride, we didn't see any opalescence. When we go, it's salt, same concentration, but it turned out that the iron form ionic bonding with the sulfhydryl groups and even making the structure more compact. So no matter what we heated, it didn't unfold.
Sorry, can you say that again?
So what happened is the presence of iron. Iron specifically formed bonding with the sulfhydryls and caused a really compact structure, so which resisted unfolding. So no matter what we heated, the protein did not unfold and denature.
So what if it was ferric iron?
Huh?
Ferric iron, like Fe2+?
That's ferric chloride. What are you talking about?
Like if the iron was like one more electron, would you still never?
I didn't know that the iron can be higher than +3.
No.
It could be ferrous or ferric.
Right. +2.
Ferrous, you mean?
Yeah.
Not +3.
Yeah.
Not +4.
Yeah.
Good question. I don't know. It might still form, but maybe not with 4, maybe with 3 or 2. So, yeah, with more charge, obviously you're going to form more ionic bonding when you have more charge. With ferrous, you might have less bonding, but we didn't test ferrous chloride. Okay, and then we added sucrose. At low concentration, it didn't have much of an effect, but at higher concentration, it increased the denaturation temperature. So this illustrates that sucrose facilitates better binding of water to the protein. So it has this kind of effect. So the cosmotrope effect. And then in the presence of acid, when the acid concentration was low,
The pH, if you look at the pH, it was 6.75. Close, or 15, 6.15. Closer to the isoelectric point. With that, when you have less charges on the protein, you have less interaction with water. So denaturation, it happens at a lower temperature. Okay? So the charge of the protein on the surface is very important and directly related to the denaturation temperature of the protein. The lower charge you have, the more prone it is to denaturation. So when we added hydrochloric acid and reduced the pH from neutral to close to an isoelectric point, we kind of, it resulted in reaching denaturation at lower temperature. However, when we added a lot of hydrochloric acid, we passed the isoelectric point. We passed it, so it went much lower than the isoelectric point. We had a net positive charge. So all of the ionizable groups on the protein carried positive charge now. And because of that, they're interacting much more with water. By interacting much more with water, we didn't reach denaturation. Okay? This illustrates that the more you have interaction with water on the surface of the protein, the less likely that protein to denature, or it would denature at higher temperatures. So that emphasizes the role of the structure of water around the protein. And if we break the structure of water around the protein will be prone to denaturation. So other than salt and pH and temperature, obviously, we have organic solvents that can cause denaturation of the protein. So all of these bonding are impacted in different ways. So hydrophobic interactions are weakened by organic solvents. So why? Because hydrophobic residues don't like the water, and when they are in water medium, they're inside, and they're interacting with each other via hydrophobic interaction. When you have organic solvents, they enhance the solubilization of the nonpolar side chain. That means, okay, so this is a more comfortable zone for me, that these residues are going to say. And they're going to open up and interact with the organic solvent and be solubilized by the organic solvent. Hydrogen bonding on the other side are strengthened. And by decreasing permittivity, because in water you have higher permittivity than you have in organic solvent, electrostatic interactions are increased as well as electrostatic repulsions. So it depends on the composition of the protein now again. So if the protein composition is high in hydrophobic, it will be impacted more in organic solvent and eventually will be denatured more readily in organic solvent than proteins that have lower hydrophobic residues. Okay? So always go back to the composition of the protein. Different proteins will have different, you will have different impact on them. Other denaturing agents can be reducing agents, organic solutes, and detergents. So reducing agents like glutathione and mercaptoethanol, they are reducing agents. So you add them to the protein, they're going to break disulfide linkages and cause unfolding. Urea and guanidine, these break hydrogen bonding. And guanidine is much more stronger denatured than urea. So at 6 molar, you get the denaturation compared to 8 molar of urea. Whereas if you look at sodium diacetyl sulfide, only 3 to 8 millimolar will cause denaturation because it binds very strongly. So at very lower concentration, you get denaturation compared to guanidine, hydrochloride, and urea. What happens here, urea, for example, forms hydrogen bonding with the protein residues and with water. So it's really breaking hydrogen bonding within the protein and hydrogen bonding of the protein with the water. And that's when you break hydrogen bonding within the protein, again, other bonds will be broken. So you can solubilize a protein using urea. You can bring it into solution using urea. Because it forms hydrogen bonding with the protein. Sodium disulfide also brings the protein into solution, and the protein carries a net negative charge on the surface. So if you notice, if some of you, those of you that do STS page, jet electrophoresis, you notice that protein originating in water is not very soluble. Some proteins are not very soluble. But if you mix them in STS for extended period of time, you see that they get into solution better. Same with urea. Yeah, with sodium disulfide, because of the binding strongly, it's mostly irreversible denaturation. I'll give you 5 minutes break.
Our last lecture, you talked about Raman spectroscopy. What or where did your lab use a Raman for that research?
Ted, the person in his lab, is Raman. It's broken now.
I was trying to use it.
Yeah, it was working at the time because he had a very good postdoc who is now a faculty member in a different department. She kept it well maintained. But when people left this lab, a lot of things broke just beyond repair, which is sad. But there are ramen in the chemistry department.
Is there any graph between the concentration of the protein and the temperature? Is it linear?
I don't know if it's linear, but I have publications where I looked at 1%, 5%, 10%. And then you see that the solubility decreases with thermal treatment as you increase the concentration. And sometimes you form a gel even. So you would denature it to a point where you actually form a three-dimensional network with a higher protein concentration.
I was wondering if it corresponds to somewhat like the water content graph, or is it more like the
Oh, I don't know if anybody looked at the relationship, whether it's linear or not. I don't remember seeing a publication on it. But I know that there is a very positive relation between concentration of protein and not denaturation per se, but the formation of polymers and the reduction in cells. Yeah, but I don't remember seeing anything that looked at linear.
Can we, someone did it from this graph, this says water content per gram of protein.
Yeah.
So
that means this is what content per gram of protein. Oh, I see what you're saying. Because obviously if you have higher moisture content, you have lower protein concentration. Yeah.
I was asking if there's some correlation with
Yeah, but if
this
you
point
see
is
here,
interesting or something.
I don't know.
Okay.
I'm not sure, but if you see here at higher water, you don't see any relationship anymore, at least with the denaturation. Kind of the maximum. But with the solubility and condensation, there's no maximum. The more you increase protein,
course, it's in a gap in terms of radiation.
Is there?
What?
Oh yeah. But there's already recording.
Are you looking for something?
Yeah, I was just looking under week 5 and the recording was here. But isn't that what we're in right now? Is week 5?
We're week 6 technically.
Oh, but lecture 5.
Lecture 6, because we did 2 lectures last week. I believe we did 2 lectures.
Oh yeah. Okay.
Yeah.
Or if you were, I'm just kidding.
Okay. You have everybody? No. Okay. Let's continue. So other means of denaturation can be physical as well, and it's very important in different applications, especially, well, not physical. I'm jumping ahead. Enzyme. I was looking at the ahead slide instead of this slide. All right. Another form of denaturation is enzymes, because enzymes break peptide bonds, and by breaking peptide bonds, you can also initiate breakage of other bonding. By splitting the polypeptide into multiple pieces, you're basically splitting it apart. So, one example in a food application is the formation of cheese curds. So it's not the gel that is formed in milk when you reduce the pH to 4.6. You form kind of a gel texture, your yogurt, which contains the water. Here you form a fused curd and expel the water. Remember the first lecture with all my show and share. So in this case here you form a coagulant, not necessarily a gel. It's a different type of a gel, but it's not really a gel because it doesn't entrap water. It actually expels water. So it's technically it's a coagulant, it's not a gel. So how does this happen? That the casein form these gel and expel water and whey proteins that is not part of this gel. So what happens here, we learned this in the dairy protein section of this course, but if you think of the casein micelle that is stable in milk, it's a quaternary structure of casein. And it has alpha casein, beta casein, and kappa casein. And we'll talk about all of them later and differences between them. And they form this kind of large quaternary structure, but it doesn't fall out of solution in milk. It is stable in milk. Why? Because you have the kappa casein mostly on the surface, and a strand of the kappa casein is glycosylated and very, very hydrophilic. So because of that, the kappa casein orient themselves in this quaternary structure to the outside. So they're negatively charged, very hydrophobic, glycosylated components of the kappa casein. So this will interact with water and keeps the casein micelles suspended in milk. Okay. Rennet or chymosin enzyme. That is that we add to the milk to make cheese. So the chymosin enzyme has a very specific cleavage site. We'll talk about that in the dairy protein section. So it will cleave a specific site that will chop off that very hydrophilic piece of caprolactone. So it gets broken off, and then the whole stability of the micelle is gone because you no longer have any hydrophilic surface. Then you have mostly hydrophobic on the surface, and then casein, micelle start coming together, forming hydrophobic interaction and also calcium phosphate bridges, because you already have calcium phosphate bridges, and that's why when you add calcium to milk, you enhance the curd yield. So you will form a strong hydrophobic interaction, expelling water out, forming the curd. So enzymes play a big role in stability of protein or losing stability. Physical denaturation. Here, the example we talked about, kneading of the dough. So basically, you have flour, you have proteins in this flour, and then you add water and you start kneading. So water and then the physical treatment that you are applying cause the protein to denature. So here you cause unfolding, physical unfolding, inducing hydrogen bonding and disulfide linkages, thus forming your gluten network. Okay? So without that kneading process, you are not really generating the gluten network. So if you just,
That physically to make them like close enough to each other. So
close enough, and you're opening the structure and you're aligning that protein in a way that they form beta sheets with each other, instead of just forming beta sheet within each protein within. When you're denaturing it and kneading and then coming in close proximity, they're forming beta sheets and also disulfide linkages. And then you're forming that network of the viscoelastic network. Beating as well, your egg protein, when you beat it, you're also physically denaturing it and allowing the hydrophobic residues to orient themselves to the air bubble, and then the hydrophilic to orient themselves to the aqueous phase, forming a film at the interface and reducing the surface tension. We'll talk more about that in a little bit here. So we talked about a lot of methods last week. Can you recall any method we talked about that is useful to assess degree of denaturation in a protein? Rachel?
SDSH?
Not degree.
Not necessarily degree. It's not a well. You can. It's a qualitative means. Yes, electrophoresis is a qualitative means. If you see polymers, you can deduce that the protein got denatured. DSC. DSC. What else? FTIR. Very good. FTIR and Raman spectroscopy. Very good. What else can you think of? Indirect.
Solubility.
Yes, very good. Yeah. When you measure solubility, if a protein is denatured, it's more likely to form polymers. There are a couple more that can be indirect. What can go down with when the protein denatures and polymerizes other than solubility? Hydrophobicity will go up, so you can measure UV absorption and fluorescence that are directly related to those hydrophobic residues, tyrosine, tryptophan, phenylalanine. So they will be exposed and your absorption and fluorescence will increase, huh?
The surface charge?
Yeah, you can actually do that. I don't have it as part of my list, but yes, surface charge will definitely go down upon denaturation.
Can you measure them with molecular weight?
Yes, you could. I don't have it here too. So instead of just running electrophoresis, you can run size exclusion chromatography to look at polymer formation. Very good. I was actually waiting for somebody to say digestibility. It will go low. It's an indirect measure. If you have an enzyme specifically, you can measure activity of the enzyme if you're looking at denaturation of the enzyme. Yeah, you said size exclusion was not here. What else you guys said that was not here and is good? Surface hydrophobicity, surface charge, yeah. Okay, so just a reminder, we talked about ramen last time. I don't remember if I showed you this example. Probably I did. But here in this example, we had the whey protein isolate and we had the glycated whey protein isolate. Yeah, I believe I showed you that when I talked about ramen. But here we heated the protein. This H is for heated and this is non-heated of whey protein isolate. And we looked at the spectra, ramen spectra, and we noticed quite a bit of changes when you heat the protein. That indicate, and that definitely we did PCA analysis and we looked at what changed, and it's an indication of unfolding of the protein. We did that at different pHs, solubilizing the protein at different pHs, and at each pH you notice different type of denaturation occurring, different bonds changing, different peak shifting occur. But when we glycated the protein and then we did non-heating and heating and we ran ramen, we saw all of the peaks. There was no shifting in the peaks, no change in the peak intensity. That indicated that glycation caused the protein to be more stable and resist denaturation. So it did not unfold. And we did that at different pH and we noticed that the spectra was the same even at isoelectric point where you have the least charges. So ramen helped us also determine whether or not that protein unfolded or caused structural changes based on heat treatment. The DSC we talked about last time explained how DSC can be helpful not only in determining the denaturation temperature, but also in determining the enthalpy. So the amount of energy it was required to unfold that protein. So it can indicate partial denaturation. If the enthalpy is low, that means the protein has been already kind of partially denatured. If there is no enthalpy at all, that means the protein has been denatured completely. And also, it gives you the impact of structural modification. So again, the same example, glycated whey protein versus non-glycated whey protein. The glycation caused a shift in the denaturation temperature by about 15 to 16 degrees Celsius. So that explained that when we heated at 75 or 80, I can't remember, we did not see a structural change in the glycated protein. So this method complemented this method. This showed us that, okay, the denaturation temperature shifted. So when we heated at that same temperature, we didn't see any change. And polymerization, you can see with gel electrophoresis, when you heat at 75 degrees for 5 minutes, 10 minutes, up to 30 minutes, you can see that you build larger molecular weights, more polymer, larger polymers that don't go down, and the monomers intensity gets reduced due to higher polymerization. So it is a qualitative method that you can see what happens with heating, but at least it gives you an indication. A quantitative method would be size exclusion chromatography.
So why does glycation help resist denaturation?
Why does glycation help resist denaturation? So, in few weeks, we're going to talk about modification of the protein by glycation. We're going to talk about all the impact of structural changes. But just quickly, because you have attached carbohydrate unit, you block a positive charge, then your net negative charge on the protein increases. then you have more interaction with water. And when you have more interaction with water, the structure resists unfolding.
Okay, so
That's very simple right now, but I will be tackling that more later on. Okay. So that concludes impact of environment on structure. Now I'm going to shift to talking about functionality and how it's impacted under different conditions. So that lecture slide, I believe, is under week 5. So my computer is not cooperating. Okay. Okay. I will save recap questions for next time because these are just what we covered right now. Okay. So, I don't expect you to know. I just want you to think a little bit about it based on what you might know about emulsification. And it's okay if you get the wrong answer, just whatever you have. Lisa, are you? I mean, I didn't read it yet, but okay. You say A. Okay. Let me clarify. What do I mean by dispersing phase versus the dispersed phase? Do you know the difference in an emulsion? You have a dispersing phase and you have the dispersed phase. So what is it, Lee?
Either oil in water or water in oil.
So can you give an example of a food system that?
Yeah, so milk is basically oil in water, and the water is a dispersing phase, and the oil is a dispersed phase.
Good.
Like basically have more water.
Sure. And what is another food system? Butter. So butter is your oil or your fat is the dispersing phase and water is the dispersed phase. So if water is the dispersing phase, that means it's the one present in higher concentration, right? So if it is present in higher concentration, do you want higher surface hydrophilicity or lower surface hydrophilicity on the protein? Hydrophilicity, not hydrophobicity. You want it lower? You want it to interact with the okay. Maybe if I can demonstrate. So this is your emulsion, and let's say water is dispersed, and you have your oil droplet. So what's forming at the interface here, the film, is your protein. So most of the protein surface area is exposed to water. So you want to have a little higher surface hydrophilicity of the protein to interact more with the water because you have more water and less oil. Okay? So B would be a more correct answer in this case. What about C? Yeah, so B and C, right? Yeah. All right. Globular proteins, and I don't expect you to know this, but let's see if you want to guess. Can form thick films at the oil-water interface, tend to form smaller, thinner, absorbed layer, can impart extended emulsion stability. Do you want to say anything?
All of them.
All of the above? You, these two are contradicting, right? Yes, Becky.
B?
Well, it's a good guess. It's either B alone or A and C. And, you have 50% chance. It is A and C. And I'm going to talk about why, but, okay, imagine this is your oil droplet. So now the oil droplet is being exploded. This is your oil droplet. If you have small, compact, globular proteins, and they go into the interface, of course they need to unfold at the interface, but you have more of them because they don't take a lot of space. And when you have more of them, you kind of form a thicker film. And with thicker film, you have better stability. And we'll talk about emulsion stability later on, but you will learn, I'm sure you've been exposed to this, that you have fluctuation and then coalescence, right? So what causes the fluctuation, that means the two droplets coming together, is not having enough repulsion between the proteins on the surface of the interface, so they come together and form a bigger oil droplet, and then the emulsion breaks and you get creaming after that. So the thicker the film, the more stable it is. That means you have less chance of getting fluctuation and coalescence. However, so smaller or thinner adsorbed layer is usually formed by an open structure protein. So let's say casein is an open structure protein, so it will extend, one molecule will extend over larger surface area. Then you tend to have, it can easily get to the interface, so it forms emulsion easier at lower protein concentration. But it's not necessarily as stable when you have, it will form thinner film, so it will not be as stable as a smaller compact protein that does not extend all the way at the interface. But again, we'll go over all of this and the mechanism of that when we talk about emulsions and proteins. Just to give you an idea, a brief idea really quick now. Okay, so what we're going to do is talk about functional properties and how they're impacted by the environment. So the definition, if somebody say, what is a functional property? What do we really mean by a functional property? So it is any physical chemical property. So it can be a physical property, it can be a chemical property, or a combination, which affects the processing of the food, it impacts the behavior of the food. And how do we judge it? We judge it by quality attributes of the food. So quality attributes can be color, can be flavor, can be texture, right? So that is kind of your technical definition of a functional property. All right. So emulsion impacts the structure of the food, the physical structure of the food. For example. Okay, and then functional property is influenced by so many factors. Obviously, it's influenced by the intrinsic factors of the protein. So the intrinsic factors, composition of the amino acid, sequence that implies structure, tertiary, secondary structure, and conformation. Is it a compact globular protein? Is it an open structure protein? The physical chemical properties of the protein, that is surface hydrophobicity, surface charge, other food components. What else do we have in our system? We have fat, we have sugar, do we have reducing sugar or non-reducing sugar? How would that protein interact with the different components that will impact a certain quality properties of the food? And the nature of the environment, which is a huge thing for pH, ionic strength, temperature. So all of this plays a role on how the protein interacts with each other, how they interact with components within the food, and how that will impact the functional properties. So this table, I admit, is really old table, and not necessarily old, not up to date, but it gives you an idea of what mechanism governs a functionality, a food application, and a protein type. What is missing in this protein type that should be there somewhere, anywhere?
Plant proteins.
Huh?
Plant proteins.
Soy. Where is soy? When I looked at this one, you're like, gosh, when did I look at this table? It's really old. I should do better looking at newer tables. But we don't have a new protein book. We have it. We need a new protein book. We don't have one, huh?
I heard you were gonna write it.
Yeah. Sure. Are you helping me?
Maybe.
Okay. Well, anyway, this is what we have. We don't have a newer table. But anyway, so what I wanted to illustrate or elaborate, which is a good table to look at and study from, is that, okay, if we take solubility, what is the mechanism that governs solubility is mostly hydrophilicity. Hydrophobicity have an impact on solubility, but what makes a protein soluble is how hydrophilic it is. How much does it like to interact with water? Okay? The more hydrophilic it is, the more net charge you have, that means it will be more soluble. What food product is impacted by solubility the most is a beverage, a high protein beverage. And the most common protein used in high protein beverage is whey protein. Now, there are plant proteins that are coming into the formulations, but originally your most favorable protein for beverages is whey protein. And so on. So you can look at all of the different ones. So for example, if I go down and look at emulsification, so adsorption and film formation at the interface. So adsorption at the interface. What is an interface? Is the division between an aqueous, let's say, and an oil. So there is a surface tension. There is a separation between oil and water. When you homogenize and there is no emulsifier, they will be dispersed, but then there will be a creaming. So they will be separated eventually. But when you're mixing, you have an emulsifier in the system, they're going to form a film around the dispersed phase, and we call it adsorption at the interface. This is how we call it. So basically, emulsification it's a mechanism that relates to adsorption at the interface, formation of the film, and that what gives you form the emulsion. And these are some application, food application, and some foods. Egg protein, milk protein, soy protein should be. Yeah, so this is just to show you the different mechanism and different functional properties, some food examples, and protein type. This will come together towards the end of the course when we learn about all the different protein types, all of the different functionalities. So then if I give you a question about a food system, what is the best protein to use in a food system, then you would know, oh, I know this about that particular protein, and I know the mechanism. I can tell you which protein to use. So ultimately, this is the hope. Okay. So if I want to divide functional properties into two categories, there is the hydrodynamic category that has to do with protein aggregation and interaction with water, and the hydrophobic category that has to do with surface activity. That means the surface activity, whether it is for an emulsion or foam, interaction with different phases based on the surface properties. So for hydrodynamic aggregation, so you have the main impact factors that impact hydrodynamic aggregation is the size of the protein and the configuration of the protein. It's globular protein, construction protein. And this controls viscosity, gelation, thickening, and texturization properties. Okay. Surface properties, that means it has to be what's the net charge, what's the hydrophobic residues on the surface, how much of those we have, and this controls solubility, water holding capacity, foaming, and emulsification. So these are the two categories of the division of functionalities, basically. And let's now dissect each one of them. Each of these functionalities. We'll start off with protein-water interaction. And your favorite is adsorption isotherm. My least favorite. Okay, so adsorption isotherm, if you had any lectures with Ted, you should know this for sure. Who doesn't know what an isotherm is? Of course, that's okay. Don't you want to switch to food science? You will learn cool stuff. You don't learn in meat science. No, not necessarily true. I'm trying to get you into the program. Okay, so an isotherm, it's a plot of moisture content over water activity. And it gives you an indication of how the water activity impact different reactions. So is the moisture content at the monolayer, the layer that is around, is interacting closely with the components in the food, or if you have high amount of free moisture or available for interaction for chemical interaction and microbial growth. That's very, very simple explanation. I will send you to Ted to explain it more, but this is what you're getting from me right now. Huh?
Is it just carve out 2 hours of your day?
Just take 2 hours? Only 2 hours of your day? Anyway, but I will break it down as it's related to proteins only. So in this case, we have 3 sections or segments or regions of this isotherm. So the first region is when the water activity is very, very low. So it's 0 to 0.25. This is where you have minimal chemical reactions or microbial growth. This is where your water is strongly bound to hydrophilic surfaces, charged groups, and polar groups. So hydrophilic surfaces can be charged and not charged, but polar. Polar meaning liking. So water in this region of the curve is, you cannot freeze it easily. It's not easily. You cannot freeze it, period. And it's not available for chemical reaction because it's strongly bound. And if you want to evaporate it, the temperature for evaporation is much higher than the temperature of evaporation for free water. So when you're determining moisture content, you really are looking at the moisture content that is water that is free water, not bound water. Okay. The next region, which is 0.25 to 0.7, here you start forming or completing the monolayer. So the monolayer is the layer of water that is directly on contact with your protein in this case. So, and you start building up some moisture layers that are not very structured moisture layers. When you start building some multi-layer water, you can then have this water be available to solubilize small molecular weight solutes and also for some chemical reactions. So in this region, above the monolayer, okay, it's very important, above the monolayer, you start having some chemical reactions occurring. And different mixtures or different powders and different foods might have different monolayer water activity, that means. That is specific for the monolayer. Anyway, but this is where you start building additional layers of water and you start having some water available for chemical reaction. Not all water, because part of the water is to form the monolayer which is the one layer of water that is bound strongly to your protein surface. The last one is where you have really high water activity, above 0.75. So here you have a lot of free water, not bound, not necessarily physically bound to your protein, or in this case to your protein. And it is available for chemical reactions completely, and it's available for microbial growth. So if we want to categorize the water and their interaction with the protein, we have different categories. We have the strongly bound water that is bound via hydrogen bonding and dipole interaction. So it is really bound to your protein. And then the strongly bound water, and then water also completing the monolayer. So this is interacting with the protein and has different properties than the free water. That means it's not really available for reactions. Entrapped water is the water that is entrapped in the matrix of a protein. So like the three-dimensional matrix of the protein. So it's physically entrapped, not necessarily bound, chemically bound. So this is a physically entrapped water that is unable to flow freely. Right? Think about a water in the gel matrix. It's physically entrapped. Not all the water in your gel matrix is actually chemically bound to your surface of your protein. Some of it is just physically entrapped. And then free water, that is the water that flows freely and available for chemical reactions. Yeah?
So when you're measuring the moisture content, are you able to measure all of the entrapped water?
Yes, you will be able to measure the entrapped water, because the entrapped water is not strongly bound water, so it will evaporate. Yeah? But it has also, okay, it will evaporate, but it really depends on how you prepared your sample. So if you want to make sure that your water evaporates, you're not going to put a piece of gel as is with 3-dimension and putting in there. What's going to happen is forming a crust. And when you form a crust, the water that is entrapped will not evaporate. Okay, so there is physical also limitations.
So is that kind of like in dried fruit, when you have like in dried fruit in the interior, that's just like entrapped water, right?
Drive-through?
I don't know, have you ever had a dried apricot?
Dried fruit. You know what I heard? I heard drive-through. Like go to the McDonald's and get a drive-through meal. And I was like, how is this related?
That's what I'm wondering.
This is what.
But in like that situation,
Dried fruit.
that would be like
Yeah,
entrapped
so
water.
sure, because when it's dried fruit, it's not necessarily. Let me think. With dried fruit, I don't know how much free water there will be remaining in the matrix, but in dried fruit, you still have a lot of the bound water too. It depends how dried it is too. Take, a date. Have you ever had the dried date?
Yeah.
Yeah. So it does have moisture still, but because it's dried, you also have a crust. You have a skin. So when you bite into it, it's still moist. So it's not completely dry. But if you have like the flat prunes, they're flatter, right?
Yeah.
So when you bite into them, there's like not a lot of moisture there. So again, it has to do with the surface and the skin you have on that dried fruit that would allow the evaporation of water. Okay, good. But that's not related much to what I'm saying.
Well, I was trying to understand the entrapped water.
That's good. Good though. It's okay. Good discussion. So anyway, so we have the bound water, we have the hydrodynamic water that is free water, free flowing water, and then the physically entrapped water. So these are the kind of the three categories of water. Okay, so starting with different protein functionalities, we talk about we'll start with water binding capacity. So which is defined as the amount of water that is bound or retained by a protein under certain conditions. That means under a specific pH, ionic strength, temperature. Okay, so what are the factors that impact binding capacity? There are many factors. Let's look at composition. So here's the predicted equation of prediction, basically. So the grams of water as a function of charged residues and polar residues and nonpolar residues. So even nonpolar residues bind water. It's not necessarily only polar residues and charged residues. But if you see here, you have a factor 1, 0.4, and 0.2. So this tells you that the grams of water per gram of protein is impacted the most by charged residues. So if you have more charged residues, you'll have much more water that can be bound, and less by polar and less by nonpolar. But they do have an impact. So again, remember, even nonpolar amino acids will bind water as well.
Is it a fitted equation or a derived equation?
Huh?
Is this a fitted equation or a derived equation?
Okay, this comes from an engineer question.
No,
What?
okay.
Fitted equation or derived equation? I'm sorry, I don't know. Do you think it makes a difference? Can you explain? Huh?
The part, you get data, then you predict the equation, but if it's more derived equation, then it's physical quantities.
Raise your voice and explain to the rest of the class.
So if it's going to be a derived equation, then it's coming from fundamental quantities, meaning whatever the value is or the environment is, that 0.4 is going to be a 0.4. But if it's going to be more like a fitted equation, then you do experiments, obtain data, then you predict the model.
Oh, I
and
see.
that 0.4 may be a 0.38 or
Yeah, I gotcha. Yeah, that's a good question, which I don't have an answer to. Maybe you engineers will potentially know this better than I do, but yeah, no. I don't know if it's fitted or predicted or whatever derived. Okay, but the point here that I want to emphasize more than the equation itself is that different residues have different impact on how much water can be bound to the protein. And mostly it goes by charged, then polar, then nonpolar residues. So that's composition. Conformation is also important. So for example, bovine serum albumin can bind 33 grams of water in 100 grams of protein. In native, but it can bind 46 grams if denatured. So this tells you when it's open up, we're exposing more residues to the surface. Even nonpolar residues will bind water, so we are going to bind a little bit more water. Okay. So temperature, I'll show you a figure about temperature in a second, but also you can enhance due to thermokinetics, so you can enhance water interaction with the protein as temperature is enhanced, but at some point it gets decreased. And I'll show you an image in a minute here. pH, if you change the pH, if it goes towards way above isoelectric point or way below isoelectric point, we're going to bind more water because we're going to get ionized amino acid groups, and these will bind 2 to 3 times more water. So at higher pH or low pH, away from the isoelectric point, we'll bind more water. Around the isoelectric point, we're going to bind less water. Salt concentration, okay, this is similar to what we talked about salting in and salting out. So a little bit of salt actually enhances water binding, But too much of salt, we are shielding the charges. We are preventing water from interacting with the protein. And presence of low molecular weight compounds such as sugars. Again, remember the impact of cosmotrophs. So if small sugars are cosmotrophs, so they're actually going to have more water interacting with the surface of the protein. So here's an example of a temperature effect. So what happens here is, if we look at the soy protein, it should be soy protein isolate. Soy protein, what happens here is with the temperature increases, we start binding a little bit more water. Again, with the thermodynamics, we have more interaction of water, we have partial unfolding, and more interaction of water even with the hydrophobic residues. But then it goes down, because at some point we start having protein-protein interactions once you get some denaturation. And when you have protein-protein interaction, you have less protein-water interaction, relatively less protein-water interaction. If you look here, which is very fascinating, and it really explains the structure-function relationship, casein. What did we say about this thermal stability of casein? Very high. Why? It has less structure. It's an open structure. It doesn't have really defined secondary, tertiary, and secondary and also globular structure. So it's less impacted by heat. Okay, the structure is less impacted by heat. So look at water binding capacity. Almost flat. Not impacted by heat. If we heat it above 100 degrees, we might have seen something. Okay. Impact of salt. Again, we see with a little bit of salt, we start seeing enhancement in water binding, and then we kind of reach a plateau where we don't see any more enhancement of water binding. But if we extended this, we might have seen also reduction in water binding. But this is just an example, and it's just for breast and thigh. I didn't find a figure that will show other types of proteins as impacted by salt. Okay, pH effect. So same with solubility curve. So pH effect, again, when we have high charges, you have really a lot of interaction with water, so a lot of water binding. And because you have here net positive charge, and you have here net negative charge. But one thing I want to ask you, see if you remember anything from your amino acid structures lecture. Why do we have higher binding here in net negative versus net positive?
Because proteins are positive when they're alkaline conditions.
Proteins are positive when?
In alkaline conditions.
Actually, proteins are positive when they are in acidic conditions, because you have your amino acids, so you have your H, R, NH3 plus, and COO minus. When you, okay, this is one amino acid, but then you will have multiple amino acids. So when you add acid, when you're titrating with acid, you're adding protons, right? So your proton is going to go here, and you will have COOH. Then the net charge is positive. When you're titrating with OH minus, with alkali, you're adding OH minus, then this will lose an H plus eventually, and this will be negatively charged. Okay? All right, so I'll give you an answer. Remember what we said about tyrosine, it has an OH group, and OH group get ionized to O minus at alkaline condition. Also, even cysteine can be ionized at alkaline conditions. So with that, with this ionization, you get even more net negative charge than net positive charge. So you will have more functional groups that are ionized here than functional groups that are ionized. So other than the amine and carboxyl groups, you have the OH and the SH that can get ionized at alkaline. So this becomes, binds more water. Okay, what is the, yes, Jason?
I have a question.
Yeah, go ahead.
So, have you ever heard DFD, the dry, I should really know the lesson. But I guess what I'm asking is, I feel like when we measure an increase in pH, the water binding isn't as great.
Jason, I can answer that.
Yeah.
I didn't get the question though.
It's so in meat you have
In meat.
DFD, it's dark, firm, and dry, and when you have a high pH closer to the physiological pH, it's not water binding as much as it's water holding because your muscle bundles are swelling, allowing for more water to be bound within the bundle rather than leached out.
Okay.
Yeah, we're
Formerly
good.
amine science person.
Yeah, I remember that now.
Well, good. All right. I'm glad you're linking it to your science. Good. What?
Probably your science.
Your science, not ours. Okay, so one last thing before I let you guys go. So what is the difference when we say water binding capacity and water holding capacity? And this is really a frustrating thing even in manuscripts. They say water binding capacity and they mean water holding capacity. So even people that write manuscript are not able to differentiate between water binding and water holding. Okay, but now that we talked a bit about water, what's the difference?
Is water binding where the water is actually like interacting with the structure, whereas water holding is more like entrapped water, like a gel?
Yes, thank you. So there are two different functional properties. One is actually bound water to the protein via hydrogen bonding or dipole-dipole interaction, whereas water holding capacity is not only the water bound to the protein, but also the water entrapped in a gel matrix. So when you have a protein powder, you don't necessarily measure water holding capacity. You might want to measure water binding capacity. But when you have a gel, you want to know how strong that gel or how strong that protein network in terms of holding water, then you would measure water holding capacity. Okay. We will continue next with solubility. And under week 5, I believe I unlocked practice set 3. So have a look. You might not be able to answer everything in there because we have not finished this lecture, but at least have a look. What I'm going to do next time is finish this lecture and divide you in half, 2 groups, and do the exercise in the class.